Our last speaker between us and lunch is Dr. Mark Silberstein, who is an assistant professor at electrical engineering in Technion. After completing his PhD in computer science at the Technion, he spent 2 years in the operating systems group at the University of Texas at Austin, working on operating system services for GPUs. He truly believes that building practical, programmable, and efficient computer systems with computational accelerators requires cross-cutting changes in system interfaces, OS design, hardware security mechanisms, storage and network services, as well as programming models and parallel algorithms. He's eagerly looking for excellent graduate students to join his efforts on emancipation of accelerators in computer systems. Okay, emancipation. I know emancipation on a different level rather than in computers, but okay. So yours till 12:30.
Sure. Yeah, thanks a lot. Let me just open the full screen here. Actually, never heard this phrase ever being spoken, so I never thought it was that awkward. But anyway, so we had a wonderful set of talks from leading people from the industry and research, and what we heard here is quite amazing, because the first part was about hardware people telling how amazingly efficient the processors are. And the second part was by software people telling how amazingly difficult it is to use that hardware. And frankly, the last talk made me a little bit more optimistic than before, but still there are gaps. And the point is that, you know, if I ask you guys what you really care about, I would guess that the answer would be you don't really care about architectures. You don't really want to hear all this system stuff like this processor and that overlapping and that pipelining. All that you want to do, all that you can get, is your application running on this damn processor and pretty fast. Now, I think that this is a perfect timing to actually show you how you can do that, and this is my whole research is about. So, this is the world as we all knew it. This is 10 years before today. This is our nostalgia for single CPU world with a single OS running on that CPU and applications running on that CPU as well. But recently, as we all heard, all those accelerators came in through the back door and became basically a masters of computer. Now, the thing that you have to notice here is that there is this unpleasant gap. But before I'm talking about this gap, let me show you that GPUs indeed matter, and I don't have to do all this propaganda here because obviously you heard enough of it. What really is important is that there is this gap, white window here. And what we don't see among all those applications accelerated on GPUs, we don't see web servers, we don't see network services, we don't see file searches, we don't see the stuff that we are actually using every day. And the reason why we don't see it is because of this very gap between the applications and the hardware. And this gap that is typically filled up by operating system is wide open, and is filled by all these hacky abstractions and various management mechanisms that everybody is building for himself, right? But previously, we used to have this operating system that helped us. So the one thing that we really want to kind of get straight, and I think that, again, the last talk was very, very vivid about it, that GPUs or accelerators are no longer a coprocessor. They're really the next, peer processors. And what it really means is that we have to change our set of mind in the way that we treat them inside the operating system and the computer system as a whole. And what that means is that we need to build a completely new or additional operating system stack, an application stack, that serves this very purpose of making GPUs and accelerators being able to access operating system services, including virtual memory, including I/O, including files and networks, and thank you for the previous question that you asked beforehand. Actually, this is exactly what we want to have. We want to have GPUs accessing networks. So what I'm going to talk about is not a hypothetical kind of idealistic vision, but a real work that we've done to make GPUs work with file systems. Now, there's a lot of stuff going on here on networking and all other I/O devices that I'm not going to talk about. I'm going to just briefly mention what we can do already today. So, GPU 101. I know you all, are great GPU programmers, but for those among you who kind of forgot what it is, here's the brief. You have a CPU and a GPU, and they talk to each other, well, most often through PCI. Now they actually don't have this PCI, but they still have this memory divide. And the way that you treat GPUs is you have a coprocessor model where you run a computation, you have it with its own state, you push some of the state to the GPU, have a kernel running there in parallel on that state, and then you get the results back. Very simple. Okay, if it's that simple, why it is that hard to build systems with GPUs? Now, I think that the answer is that the GPUs are kind of isolated from the rest of the system. What we have here is a lot of effort being done by developers to do data transfers, invocation, memory management, whatnot, and a lot of effort from hardware vendors to actually allow us to run efficient parallel algorithms, which is great. But we really need to take care of that big part that occupies a lot of our time. Let me show you a quick example for those who is not yet convinced. So let me show you this very simple example of photo collage application, which we want to accelerate because it has two very compute-intensive calls, decide placement, remove outliers. So these calls are very compute-intensive, and we want to put it on GPUs. But we also have this nasty code which calls read next image file. And obviously we cannot put this whole kernel on a GPU because we have this call here. So what it takes is actually to break our application into pieces. Some of it put on a GPU, some of it leave for a CPU. And the way we put application to GPU is actually to really break it into the kernel, into the main part, and have the kernel being invoked, and have all these data transfers and kernel start determination and iterations and whatnot. Now, this is all really unpleasant part. Of course, if we had HSA, we wouldn't have to do that. But it wouldn't save us from actually dividing our program into these parts. Now, of course, it all is great, but we need to take advantage of our abilities as engineers to make it even better. So the way to do that is to hide the overheads that we have here with invocation latency and transfer overhead and synchronization and whatnot. And all these overheads keep us busy to actually build this program into something that runs really fast. So the way to do that is obviously to apply a whole bunch of different techniques that we all know, like asynchronous invocation, data reuse, double buffering, buffer size optimization. Everyone who ever worked with GPUs knows exactly what has to be done. Now, everyone who didn't work with GPUs doesn't want to know what has to be done. That's the problem. And what we really don't want to know is we don't want to know all this stuff. We don't want to care about it at all. And the question is, why do we still have to? So here's the answer, right? I can wrap up my talk here. GPUs are P-processors. They need I/O operating system services. So the idealistic view of the system that I have in mind is the one where I have a whole bunch of processors, and they all access the file system as if it was, CPU, GPU, who cares? So what they have here is they have a system-wide shared namespace, obviously, which means that if you open a file on a GPU and read it and also write it from a CPU, you want both of them to see the same file. You want very similar API as CPU, open, read, write, close. And you want to have a persistent storage because that's what file systems are all about. So let me show you why it really changes the game here. What it changes is that, as you can see, CPU is absent from this picture because GPU can handle everything himself, right? So GPU can open, read files, perform open and read calls from inside the code. It can do read-aheads. It can do all different kind of optimizations that the operating system is doing for you today already when you run your programs on CPU. It can do automatic overlapping of computations and data transfers. It can do data reuse. It can do random data access. It can do, everything, just maybe not, brew coffee for you. But the point is that this simple observation, this simple service allows your program to become fully GPU-based. And it's my job as a systems developer to take care of the performance optimization without you having to do that yourself. Now, can you build that really? Yes, you can. But before I show you how to build it, I want to get some, very small things straight what GPUs are. There are three things that make GPUs very different: parallelism, low serial performance, and heterogeneous memory. So in terms of the parallelism, what we have to think about a GPU, when we think about GPUs, is actually a multi-core machine, right? Because what it has is a bunch of cores that are all connected to the same GPU memory. This is very, very similar to multi-core CPU. What really matters is what we have under the hood in every core. Because in every core, we have a bunch of SIMD vectors that are all operating at the same time in a data parallel manner on the data. Now, what really is making GPUs is this very, very deep high-throughput parallelism, high-throughput pipeline that they have. So let's take a look at what happens when the GPU thread accesses memory. When it accesses memory, it is stalled. It gets stuck. But there are other threads around, so what GPU does, it switches to another thread. And this other thread goes back to the memory and also issues some memory request. And then, if it gets stuck, then there is another memory request, and so on until we run out of threads. But then, hopefully, we have our first request being served. And then we can just simply use the results. Okay? So what makes GPUs very efficient because they don't rely on caching. They actually maximize the memory requirements and they maximize the device utilization, the ALU utilization, by means of switching between different contexts. Now, if we put all these things together, we have three levels of parallelism that all of them we need to utilize together in order to get high performance. So we have data parallelism, we have thread parallelism, and we have task parallelism at the multi-core level. Now, how do we put software on this hardware? Well, obviously, there are different models, but the OpenCL and CUDA take the stance that every unit in SIMD vector becomes a thread. So how many threads would we have? Well, a hell lot of threads, actually. If you take an NVIDIA K20X GPU, you get more or less 28,000 threads invoked at the same time. Now, it doesn't mean that every thread actually as fast as CPU thread, but it is still a lot of threads to keep in mind here, right? And that means that without that number of threads, you will not be able to get high performance. And this is the crux of the whole thing, right? The single GPU thread is about 100 times slower than the single CPU thread for very basic operation. If you try to run, let's say, a vector, inner vector product, right? And you want to compare a CPU thread and a GPU thread on your CUDA processor or whatever other processor, I believe, you would get about 100 times slower performance. So you really have to have a lot of threads. Now, another kind of painful part of GPUs is that discrete GPUs in this case have very high local memory bandwidth but very slow remote access. So if you take a look at this as really multiprocessor non-uniform memory access architecture, you have extremely non-uniform access because GPUs have 250 gigabyte per second bandwidth, whereas GPU accessing CPU memory goes down to about 12 gigabytes effective. Now, I didn't manage to get more than that from PCI 3, I must say, but maybe I'm doing something wrong. Now I think we are all ready to see what we actually did. So what we did was to really revamp some part of the file system stack to allow GPUs to use files. That required modifying file system semantics a little bit. That was also, we also did some relaxed distributed file system consistency logic. And again, I'm not going to get into all this nitty-gritty details. What is really important is that this is the program that you can run on your GPU today. And if you look for differences between that program and your CPU program that simply reads the file and does some computation and writes the results back, is the letter G by every single API call and not anymore, anything else. Okay? So this is the goal, right? GPUs do CPU API calls. Now, what is important to take a look here is that we have complete support for GPU internal idioms to work with. For example, support for shared memory. You can use shared memory to store your temporary data in user space. We basically adopted the parallel API calls model where given a read call, we don't really want to maintain a file descriptor. We don't want to serially to do increments, one after another to serialize access from different threads. We provide explicit offsets. Some of the calls get really cached, so effectively when you perform open call from GPU, only the first one gets down to the CPU and all the rest get cached. So in principle what you get is very fast, many open calls, and that's what helps your programming simplicity to actually be possible here. Okay, so there are a whole bunch of different features that our system provides, and what we think is that the key issue here is that what you can get from GPUs today is very similar to what you can get from CPUs. Now, if you look inside how this whole thing was made possible, you have a system which has a GPU file system library that is linked to your GPU code. You have a system that has GPU file system hooks invisible to the programmer. They're all inside the operating system kernel. And you have a GPU file system distributed buffer cache that spans all memories in both GPUs and CPUs, and all of that is managed and completely under the hood without a programmer being involved at all. So the GPU file system library is taking care of handling massive parallelism, and the non-uniform memory is being taken care by the distributed buffer cache. Now, I'm a little bit cheating here because it's not completely transparent. It is transparent after you get used to certain constraints that we introduce here. And these constraints are, we believe, required to get something useful from GPUs together with the file system. So, the first question that we faced was, you have a GPU and a CPU, and you want to allow file access, and basically what it means, you have to cache some data both in GPU memory and CPU memory. And then the question becomes, if I cache some data in GPU memory, and then CPU access that data, what kind of data the CPU has to see? Should it be exactly the same up-to-date state? Well, if you ask me, idealistically, yes. but practically no. So the concern is that if we look at the system, the latencies and the bandwidth limitation involved are very, very, very high, right? So the GPU has very long latency operations through PCI to get to CPU memory, and very much smaller bandwidth, as I said. So what we had to decide was, how do we actually allow open, close, read, write without having to pay this latency all the time? So the way to do that is to loosen the consistency, meaning that now when GPU opens a file, it can work on it as much as it can, as it wants, but CPU will not see the updates. But only after the GPU closes the file, the updates get propagated back to the CPU. And this is the same way the other ways, right? So no matter if you have a CPU or GPU, this is the behavior that we guarantee. Now, you can say that it's very difficult to program that way, and you would be right. But the thing is that for file systems, those who program and write files today are already doing that anyway. The thing is that today, if you access NFS and you open two files from two different hosts, the file updates from one host will not immediately propagate to another one. But the question is, of course, we're not talking about a network file system. We are talking about single host. So it's still inconvenient, right? Well, yet, although physically it is the same machine, practically these are two different machines. And we have to treat that as a distributed system with distributed system protocols in order to take advantage of the computational capabilities of those machines and not waste our time on synchronizing between the data between those two. So let me spare a little bit of implementation bits. So the GPUFS API and file state and buffer cache and everything is managed on GPU. And there is an RPC daemon sitting on the CPU side and GPU file system consistency model sitting in the operating system kernel. Now, what I want to talk about a little bit is how we perform the CPU-GPU RPC. So the way it works is that we have a CPU memory, CPU which runs a certain RPC remote procedure called daemon, and we have a GPU, and so GPU kernel asks the CPU to read some data and to bring it over. Now, I want to remind you that in the previous talk there was this CPU callback property of HSA. This does not require CPU callback property. It actually works on GPUs that are not HSA today. Now, once the data gets loaded on the CPU, it goes through the staging area and then just moves directly to the place where it will be used by the GPU in the buffer cache. So what is really important about this picture is not how it is actually implemented, but it is the conceptual fact that we basically reversed the way GPUs are conceived in the system. Because typically GPU is a slave, right? We ask GPU to do something for us. Here, we make it the other way around. We ask the CPU to do something for us for GPU. So there are a whole bunch of other things. If you want to read the paper, you're welcome. I can give you the link, or you can find it on my website. Right, so, HPC people among you would definitely want to hear that the overhead is huge and nobody would use it. Well, turns out the overhead is not huge, and hopefully people will start using it at some point. What is really important, and the main reason why starting using it, is because now you can write completely GPU programs. No CPU code whatsoever. And this is what we demonstrated in our benchmarks that we wrote to evaluate this system, and this is what you can also find in our paper. The point is that all the benchmarks were written completely inside GPU, inside CUDA. They have no single line of CPU code being written by a developer, right? We obviously have some CPU code running there. So just to get you some, sense of how well it runs. If you take first of all, it runs on multiple GPUs. As I said, the buffer cache is managed to cross GPUs as well. So if you have a certain approximate image matching algorithm that queries a certain database and reads the data from here and there and tries to stop reading the data whenever it doesn't need to read it anymore. So this algorithm is not hugely efficient, but it runs 6 to 9 times faster than 8-core CPU on 4 GPUs. Now, a simpler example is to run a string matching from a certain dictionary on Linux kernel tree with about 33,000 files. All of these files are kind of small and nasty to read from GPU, but the point is that although we are using GPU file system, we can get about 6 to 7 times faster performance than on 8-core CPU, and the GPUFS overhead is about 7%. Now, we are working to make it even better than that, but we should notice that the workload itself is extremely file system intensive. So, to summarize, and I hope I'm right on time, GPU file system is the first file system to provide I/O for GPUs. We are working on a lot of other things. Among others, we are trying to do the same with HSA kind of architecture. We're trying to show that it is still worthwhile to use specialized file system access architecture directly from GPU code. We are working with some vendors, with Mellanox and with Fusion IO to build something that actually merges GPU and allows direct access from GPU to the device itself, so that we can do networking, we can do file access directly from device without having to pass through the CPU. And I guess there are all other processors around that we also want to use and want to show that this architecture actually would work. So with that, to summarize, I think I already summarized. So yeah, emancipation of GPUs is here. If you want to talk to me, please feel free. And if you are from the Technion by any chance, make sure that you attend my class next semester.
We now have lunch. 5 minutes? Oh, we have room for 7 questions because we have 7 minutes left till the food gets set up. Just as after we finish here, after the questions, there's lunch outside. For those continuing to the training session in the Dan David building, it's about a 5-minute walk. I will be going ahead to help set up, but feel free to hang around here and eat till 1:30, but we start promptly at 1:30, the training session. But let's start with the questions to Mark. Go ahead.
Have you submitted this GPUFS to the kernel?
Well, fortunately, it doesn't require much kernel changes, and we haven't. As a matter of fact, it's all user space. Yeah. So the file system. So that's a great question. At the moment, they're actually all managed by the CPU, and GPU effectively, as I said, uses the CPU as a remote server to provide the data, to actually manage this metadata. But it's going to be changing very soon. Yes, for now it's basically a software layer that does not get into the file system itself. But again, as I'm saying, it's going to be changing soon. Yes.
When you look at it from a cluster point of view, when you slide very quickly, you can't get rid of the CPU because you need to do other communication and synchronization and other things. So what were you planning? To move it all into the GPU, or to have some synchronization mechanisms between CPU and CPU?
Okay, thanks for the question. If I understand. Okay, yeah. So if I understand the question correctly, I kind of was caught on cheating that, more or less, that, I want to get rid of CPU, but I can't. So I still will be using CPU at some point. Yes. But you as a user will not have to take care of that. And at the point where GPUs will be mature enough to take some of the code or entire piece of code on GPU, I will do that for you without you actually knowing that.
Do you see an MPI
Yes, as a matter of fact, we already have a socket library on GPUs in sort of, I don't know, even not alpha, but whatever pre-testing phase.
Does it make more sense to utilize the network processor to combine with the GPU for that?
That's what we are doing. Thanks for the hint.